Hi guys, today we're going to learn about the volume by the shell method or using cylindrical shells. To find the volume as y equals f of x when it's revolved around the y-axis by disk, what we were doing before, it was that the slice was an horizontal rectangle and we were looking at the cylinder formed. Today what we're going to do is to find the volume of the same solid but using the shell method. What we're going to do is we're going to look at a vertical rectangle revolved around the y-axis. This would form a hollow-out cylinder, or what we call a shell. The shell, I'm showing you here the situation of the shell, okay? Please remember that when we were doing discs or washers, your representative rectangle was perpendicular to the axis of rotation. Here, your representative rectangle is going to be parallel, and I'm indicating here the shell because that should remind you of the parallel symbol that you learned back in geometry. So you know that when you see the shell, the representative rectangle is going to be parallel to the axis of rotation or axis of revolution. Now, in the situation that you are seeing here, you have that the axis of revolution is the y-axis. In addition to that, this distance that you have here is not necessarily x. We're going to call it r of x because it's a function of x. Sometimes it's going to be r of x, but sometimes it's going to be something different. This one is going to be your height. Okay, instead of calling it f of x, I'm going to call it h of x. So what you have here is, technically speaking, okay, a cylinder. What we're going to do here is you're going to cut it somewhere and stretch it up, and you are going to have a situation like this. As you can see, this 2 pi, instead of the x, we have that it's r of x, and instead of f of x, it was h of x. Please note that in addition to have like the cylinder that we do have, we have a depth. Back in the day, when you were in geometry, you learned that the surface area of a cylinder, it was 2 pi, and then you have that it was RH plus 2 pi r squared. Since this cylinder that we're seeing, it's hollow, it doesn't have top and bottom, that part we don't take in account. Now, this surface area, this was a 2D figure. This one that we're seeing here, in addition to have the 2D situation, this one and this one, pretty much the height. This is what you are seeing, and that's why I changed it to h and r, so it's connected to your surface area formula. In addition to that, you have this one that it's the width. Okay, so do you see it there? So in addition to that, to make it a 3D, the length of the solid is going to be 2 pi r squared, not r squared, r, and then the height is going to be h of x. The width of the solid is going to be delta x. So to connect all of these 3 measurements, what you're going to have that is the volume of the solid, technically speaking, is going to be 2 pi r of x times h of x times delta x. Do you agree with that? The issue with this volume, to get the exact volume of the solid that we have, if we have infinitely many shells, what you're going to have is you need to put a summation, okay? If you have a summation here and we index my x's here, okay, what you're going to have here to get the exact value, you are going to take a limit when the delta x approaches to 0, because you want this to be very, very thin and to add all of those, okay? So instead of that, because that one, you know that that one is screaming a Riemann sum, okay, in a way, okay? What we're going to do here is we are going to convert that Riemann sum into a integral. You know that when we have Riemann sums, we end up with integrals because they are simpler and they are more user-friendly. So the volume about a vertical axis by shells, the formula is going to be volume is equal to 2 pi, and it's going to be from A to B. Those are going to be x values, and then it's going to be r of x times h of x dx. Please note something. Here, the values that you are seeing here, they are not magical. This 2 pi is the same 2 pi that you see here. The r of x is the same r of x that you see over here. The h of x is the one that you see here, and the dx is an approximation. You know this because we already did linear approximations of the delta x that you see here. Okay? Now, you are going to tell me, how about if we are looking for the volume about an horizontal axis by shells? Well, as you can imagine, that one, instead of having x's, you are going to end up working with the y values. Okay? So that's going to be another possibility that you might have. Okay, you're going to tell me why we're learning shells if we already know discs and washers. Sometimes working with shells, when you're working with axis, it's easier. Okay, so a vertical axis, it would be the y-axis, and this one, it would be also the x-axis. Okay, now here are the meaning of, here's the meaning of each of the situation, okay? So the radius, r of x, is going to be the distance, okay, between the rectangle and the axis of revolution. So this is going to be a new thing, very important for the shell method. The height, h of x, that you see it here or here, is going to be the height or the length of the rectangle. Okay, so that's what we are going to have, and it's very similar to the base that you had when we had cross sections. It's very similar. Okay, so some things to remember. With the disk method, the representative rectangle is always perpendicular, okay, to the axis of revolution. With the shell method, the representative rectangle is always parallel to the axis of revolution. So that's a big difference, okay? So it is usually easiest to use disk about the horizontal axis and shells about the vertical axis. That's when it's the easiest. If you do this, you're going to end up working with x's. You're going to tell me why it's easier. Well, we are used to work with x's, okay? So that's why. Okay, if you don't mind and you don't mind working with y's, then you can use either or for the other situation. Here's the other situation. If you use disk about the vertical axis or the shells about the horizontal axis, you will end up working with y's. Okay, so that's what we have, and hopefully this explanation makes sense. Okay, so let's move on to some of the examples. For the first example, what we have is we want to set up an integral expression that can be used to find the volume when the region is bounded by y equals x squared plus 1 and y equals 0, and when this region is rotated about the given axis over the interval 0, 2 by using shells. Please note that we need to use shells. Okay, so for the first equation, you do have, okay, for both of them actually, you do have a quadratic equation, something like this. Okay, and you know that the vertex is at 1, so you have the 1 here. Then the y equals 0, you are going to have that your y equals 0 is going to be somewhere here and here. Okay, and then you have the 0 and 2. So the 0 and 2, you are going to use them, okay, as boundaries of your region of interest. Okay, so the first thing that you are going to do is finding your region. Okay, so this is the region that we're going to be rotating. Okay, this is the area that we're going to be rotating. So you have that this is 0 and this is 2, where we got that from the interval that they are giving you here. Please note that this point is 0, 0, okay, this point is 2, 0, and this point over here, you plug the 2 there, and you can find the value there that we don't mind, okay? So, but anyway, you know that that point is going to be, what's going to be that point? 2,5, okay? So, FYI, okay? Anyway, so we have X, we have Y, okay? And what's the axis of rotation? The axis of rotation here is your y-axis, so let's draw it there. That's your axis of rotation, okay? So rotate that one. So now that you know that that's your axis of rotation and we want to work with shells, what are you going to do? You need to make sure that you create a rectangle that it's parallel to the axis of revolution. Parallel to the axis of revolution, it means that you have a vertical rectangle. Imagine that that line that I just drew, it's a vertical rectangle. So what you have here is we're going to be working with x's because that rectangle that you see is vertical. In addition to that, you need to find first your height. Your h, the height of that rectangle that you see, the top is going to be this quadratic equation, and the bottom is going to be 0, okay? So you have that it's x squared plus 1 minus 0, so you have that that one is just going to be x squared plus 1. Now, here the key is the r of x. The r of x that you have from the formula, you're going to tell me, how do I know the distance between the axis of revolution and my representative rectangle? So your representative rectangle is somewhere in the x-axis. That's as far as we know. If I draw the line here, it's going to be here closer to 2, but it could be here. So it's not a fixed number, okay? So that's going to be in the position x. So it's going to be x minus 0. Why minus 0? Because your axis of rotation is the y-axis. Do you see it? So this is going to be just x in this problem, okay, in this specific problem. So then you are like, okay, so we have all the pieces of the puzzle. We can pretty much apply the formula. Your formula is volume is equal to 2 pi integral, and then you have the h of x, which is x squared plus 1 times x dx. Now the question is, what are the limits of integration? We're working with x's, so your eye should go to the x-axis and see the shaded area. You have that it's from 0 to 2, okay, and that's what we have, okay? So that's your setup. I would leave it like that. Of course, you can distribute, you can integrate, you can do a lot of things that you don't need to. Okay, so let's move on to the part B. Part B, you do have exactly the same shaded area, so you can just reuse the data that we have from A, okay, because it's exactly the same problem. So we have that this is 0, 0, this is 2, 0, and this one was 2, 5. Okay, obviously this is X, this is Y, but what's the difference here? Your axis of rotation is Y equals negative 1. Y equals negative 1, let's say that it's somewhere here. Okay, so you can see something further there. X equals negative 1. When we had a disc or washer and we had a hole, okay, yesterday and the day before yesterday, you had a different formula for the washer and the disc method, right? But here, the same formula will apply, okay? That's the user-friendly situation about the beautiful shell method, okay? So your axis of rotation is this one, so your representative rectangle is going to be parallel to that axis of rotation, so you have a situation that looks like this. Do you see it? So this is going to be your representative rectangle, okay? Which means that we're going to be working with x's because that representative of rectangle is vertical, okay? So what you have is you have h of x is going to be equal, and you're going to tell me, is it the same as the one before? Yes, the height is the same, right? It depends on this function, okay, and on this function as well. So makes sense that it's the same. Now, what's going to be different here? What's going to be different is the distance between the axis of revolution and your representative rectangle. You know that this distance is going to be from negative 1 to x. So this distance is going to be, if you see it left minus right, okay, what's on the left? X. Okay, please remember that this, the position of that on is x, so x minus minus 1, and surprise, surprise, your r of x is going to be x plus 1. Do you see the big difference between this one and this one? Hopefully you do, okay? Obviously this is bigger, the distance is bigger. Why? Okay, because this distance is longer than this one, okay? You see it? Now, you have, again, all the pieces of the puzzle, so you have volume is equal to 2 pi integral, and then you have that it's going to be h of x, which is x squared plus 1 times x plus 1 dx, and then what are the limits of integration? Again, you have, technically speaking, something very similar to the shaded area before, using this and this, so 0, 2, and that's what we have, okay? So hopefully it makes sense, okay? Let's do more examples so you can feel very comfortable using the shell method, okay? So the next example that we have over here, you need to set up an integral expression that can be used to find the volume when the region bounded by y equals root x, y equals 0, and x equals 4 about the given axis using, again, they want you to use shells, so that's fine. Okay, so let's set up your situation here. Okay, so the first thing that I see is these two, they are going to be, technically speaking, the same area. Okay, the only thing that changes is the axis of revolution, so let's draw them at the same time. So this is going to be your square root function, okay, y equals root x. Then you have y equals 0, which is going to be your x-axis, okay. Y equals 0, the x-axis. Obviously this is going to be your y-axis, but that's not a boundary. And x equals 4. So x equals 4, let's say that x equals 4, for making it easy, let's make it here. Okay, so let's label it x equals 4, x equals 4. Okay, so you have that the shaded situation here. Now it's more clear which shaded situation you have here. Okay, so this is going to be the area that we're going to be rotating. Okay, do you see it? Okay, so that's what we have. Anyway, so about the given axis using shells. Okay, so this one, the first one that we have over here, is x equals 7. So where's 7? Well, you start with the situation that this is 0, this is 4, so 7 must be further here. Okay, non-proportional to the situation, this is going to be x equals 7. Okay, but don't worry, well, you can see that there's a humongous hole there, so you can see what's going on here. Anyway, okay, so that's your axis of rotation. So your axis of rotation, remember the shell is going to be parallel to the axis of rotation, so I move my ruler here, okay, having my representative rectangle over here, so you can see your beautiful representative rectangle here, right? Okay, so you're going to be working with x's, y-axis, because your representative rectangle is vertical, okay? So what you have here is that h of x is going to be equal to top minus bottom. The top is going to be your root x, your bottom is 0, so h of x is going to be just root x. Now, the one that we have here is r of x. What's the business for r of x? R of x, you know that the position of this one is x. It's always going to be right minus left. On the right side, what do you have? Oh no, the axis of rotation. So that goes first, 7 minus x. Okay, so that's going to be your axis of rotation. Why this happened? Because the axis of rotation was on the right side of the area of interest. Do you see the difference between this one and this r? Okay, so the position of the axis of rotation, as you can see, very important for the r. Okay, now what's going to be the volume? Well, you know that after that, pretty much we can just apply the formula, 2 pi. Remember that the shell is 2 pi, okay? So now we're working with x's, so you're looking at your x's here, so it's 0, 4, and then you have that it's going to be square root times 7 minus x, and then dx, and you're done. Isn't that nice? So I really like the shell method. As you can see, once you see that crazy r of x or r of y that you have, everything is pretty simple. Okay, so let's look at the situation, because this one is going to be a little bit different. As you can see, this one we have y equals 5. Okay, so we have that this point is 0, 0, this point was 4, 0, and then this point over here, it must be 4, 2. Okay, so you see that because I plug it back here. Okay, if you're wondering when the world she got that square root of 4, it's 2. Okay, so we know the intersections. Otherwise, you would set them equal, this, and then you plug them in. Okay, so that's how I got them. Anyway, you have this, what's your axis of rotation? Y equals 5. Okay, so the y equals 5 is going to be an horizontal line that is going to be a little bit further from the region of interest. So this is going to be your axis of rotation. Okay, so that is your axis of rotation. Okay, what happens here? Well, as you can see, the axis of rotation, oh no, that one is going to be horizontal. So it's going to be, your representative rectangle is also going to be horizontal. Why? Because it's always parallel to the axis of rotation. So there you go. So what this is telling you, when I draw this one, I'm like, oh, I'm going to be working with y's. Okay, so everything should be in terms of y in this situation, starting with your h of y. Your h of y, you know that you are going to work with, this is going to be your right and your left. Okay, so the right is fine, it's a 4, but then you have that the left here is not going to be root x. You know that root x, what's going to be that? You square both sides, so it's going to be x equals y squared. Okay, so this is going to be y squared. Where this comes from, because you know that y equals square root of x. If you square both sides, you get this one. Okay, and you need to be working with y's as the independent variable all the time with when you have horizontal representative rectangles. Okay, so r of y is going to be equal to, you're going to tell me, well, in the other one my dummy variable was the x, what's going to be here? Y. Okay, we are not very original here. So this is going to be in the height y. Okay, so what do you have here? You have top, which is what? 5 minus y, and that's going to be your r of y. Isn't that simple? Okay, why that? Because the axis of rotation is above the area of interest. Okay, so it's 5 minus y. Okay, now we have all the pieces of the puzzle. So you have the volume is equal to 2 pi integral of something, okay, and then it's going to be 4 minus y squared times 5 minus y dy. Now the question is, what do you think that are the limits of integration? Are the limits of integration the same as here? And the answer is no. Why not? Because now we're looking at the y's. What is the lowest point with respect to y? 0. But what's the highest point with respect to y of my shaded area? It's going to be 2. So that's why we have the 2 over here. Do you see the big difference of the limits of integration? And that's what we have. Isn't that cool? So let's move on to the last example of the day. Okay, so you can compare and see what's the situation here. And here I'm just going to set it up. Okay, so you can see the setup of both. Okay, we're going to set up the volume of the solid generated by revolving the region between x squared equals y equals x to the power of 1/3 about the y-axis. Okay, so let's start with graphing my parent function, quadratic function here, and then if you remember this one, it was also a parent function from algebra 2. So you have a situation that looks like this. Maybe you tell me, hey, I don't remember that much about algebra 2. I prefer to do it algebraically. Could you do it algebraically? Yes, technically speaking, what you can do Okay, here I'm going to do it sideways here. Okay, what you can do is you can set, okay, your x squared equals to x to the power of 1/3. Then what you're going to do here, don't divide anything. If you divide anything, something, you know that you're going to end up losing information, so don't. Okay, do this, then factor. You are going to factor the x to the power of 1/3, and then you have x to the power of 5/3 minus 1 equals 0, and then you can see that your intersections are going to be x equals 0 and 1. Okay, so algebraically speaking, you can also do it if you don't see it like with the graph. Okay, so you know that this point is going to be 0, 0, and if you don't know where I got the y, I plug the 0 into any of the equations and I got the 0, and when I plug the 1 here, you know that this point is 1, 1. Okay, so you already know that. Please remember that my graphs are not proportional. Okay, so it's just like a rough idea of what's going on, so we have the great idea and we can see the graph. Okay, so in this situation, okay, the area of interest that you see is the inside of this, and okay, you have this. Okay, so we have the situation. Now, what happens here? Your axis of revolution is the y-axis for both. Okay, so we have them here and here. That's your axis of revolution. Okay, but the difference here is I'm going to use shells for A and then discs for B. Okay, so that's what you have. Okay, so with shells, let's start with shells. The shells is parallel to the axis of revolution, meaning your representative rectangle will be there. Okay, so what's the business here? Your representative rectangle, okay, it's going to be the height of that representative rectangle. We're going to end up working with x's. So h of x, the height of this representative rectangle, you have that on top. You are going to have the x to the power of 1/3, and the bottom is going to be the quadratic situation. So you have this. Now your r of x, what's going to be your r of x is going to be this. Remember that it's in the x position, so it's x minus 0, which is just x. Okay, and then your volume is going to be 2 pi integral from 0 to 1, specifically is this 0 and this 1. Okay, and then you have that it's going to be x to the power of 1/3 minus x squared times x dx. Okay, so you have that for shells. Now for discs, what is going to be different? How we were doing this differently? Well, let's refresh your memory so you can see it. Okay, so you have your axis of rotation, same, the y-axis, but disc is perpendicular to the axis of rotation. In addition to that, your r's are going to be touching the axis of rotation. With shells, they were not doing that. So you're going to have a big R and a little r. Do you see it? So what's the issue here? I'm going to be working with y's because I can see that my representative rectangles here, what happens there? They are horizontal. Okay, so you're going to have two r's, right? Big R and little r. In addition to that, you need to change your equations and make them with respect to y instead of x. So if I square root both sides here, you have that x is going to be the square root of y. And you might ask me why you are only selecting the positive side when we have that it was plus minus, because this is in quadrant 1. That's why I'm just selecting, okay, that this graph that you have over here is x equals to root y. On this side, what are you going to do to clean it up to leave x alone? You are going to cube both sides, so you have x is equal to y to the power of 3. Okay, so now with that being said, and with the changes that I did to my equation, so I have a different independent variable, what are you going to do? Your big R of y is going to be the distance of the axis of revolution to the furthest point of your orange area. So it's going to be this one. What is this one? That's going to be the square root of y minus 0, because this is your y-axis. So it's going to be just root y. Little r is going to be the distance between the axis of rotation and pretty much the beginning of the orange section, which is going to be whatever function is this one. This one is going to be what? Y power 3, because that's right minus left, minus 0. So you have that this is y to the power of 3. So this volume is going to be different. Why? because you know that this is going to be just pi, the integral, and then you have that it's big R squared minus little r squared and all of this dy, and then you're going to tell me what are going to be my limits of integration. Your limits of integration are going to be based on the y's. So you're going to look at this one and this one, so it's 0, 1. It seems that they are the same, but we're getting the 0 and the 1s from a different spot. Do you see them? Okay? And then these two are two polynomials, so it's pretty straightforward to integrate that. Okay? So I hope that you find this video helpful. Bye!